All right, dear student, here I am again, Dr. Carver. We're going to talk about another chapter for 1406. By the way, 1408, which is no major biology, shares some of those contents. But for 1406, some of the contexts that they are within these chapters are more in details. So let's talk about the chemistry of life, the nature of molecules, and also we are going to talk about water and the properties of the water. You are never going to think about the water as water you are drinking. You are going to know the properties of the water and what is water and how a molecule of water make this molecule of water can make water that you are drinking. So let's talk about the first part of this chapters, which is the chemical context of life, from atoms to a molecule. So this so this um, this part is going to focus on the chemical compound that make a matter. You know what is matter? Matter is anything that makes up a space and has a mass and a volume. Matter can be solid, liquid, gases around us, and within our body. So the first part, exactly, we are going to focus on the atom, element, and molecule. Is that making some things to you? You remember chapter 1? You remember this slide? The hierarchical level of organization in a living thing, where you see what I circle in red. This is where what we are going to focus in this chapter. We're going to focus on the particles that make atom, that make a molecule. And remember that each level of organizations, we have an emergent properties. We have a property that doesn't exist before, exists after. So let's focus on carbon, for example. Carbon is made of electrons, neutrons, the three major particles of which atoms are composed: electrons, neutrons, protons. They came together to make atom, which is carbon, and carbon can make to make a molecule with another oxygen, another oxygen to make CO2, for example. So this is CO2 has a property that the atom carbon by itself and the oxygen as an atom by itself is not doesn't exist before. Or let's talk about the molecule of oxygen that we breathe, right? O2. O2 is made of two atoms of oxygen, O and O. Atom of oxygen by itself is not the molecule of oxygen. This is different property. O, it's a gas. O is just an atom that will make this gas that you are breathing. Oxygen. Element is the smallest form of an element is an atom. An atom bound together to form a molecule or compound, right? An element is very unique. He has a unique number of protons. An element, if he has, like for example, a number of proton 10, you are not going to find another element that has 10 proton. Only this element has this number of 10 as a proton. So the number of an element has a unique number of proton, and but the element they are and it has a property that is completely different from other elements, chemical properties, I mean, okay? And an element, you cannot break it. Can you break carbon? You cannot break it down into substance by chemical reactions. And compound can be made by one similar element that they came together. They have to be an element to be and compound to be a compound or molecule has to have at least two identical or different two identical element or different element. Two or more, they can come, like molecule of glucose, for example, C6H12O6, the sugar that you are eating, right? Sugar, our table sugar, C6H12O6. How many atoms are there? You hear C, you hear H, and you hear O. So they have carbon, hydrogen, and oxygen, right? So in a cell, the salt in a cell is Na, which is sodium, and chlorine, all right? So this is, and the sodium is a metal, and the chlorine is a gas, it's a poisonous gas. Sodium in contact of water is a metal, it explodes, dangerous. Chlorine is a gas, but coming together, look at that, they make sodium chloride. What did you see here? This is an atom with another atom. That they are both dangerous. They are both poisonous. But coming together, they make NaCl, which is an emergent properties because the property now of sodium chloride, which is essential for life, it's the salt table, doesn't exist before. So when they came together, they make sodium chloride, which is an example exactly of emergent properties. So an element has a chemical symbols. Either we put the first two letters or the first letter. So this is a list of the elements that I want you to memorize their chemical symbols. Carbon is a C, hydrogen is H, oxygen is O, nitrogen is N, phosphorus is a P, sulfur is S, sodium is Na, potassium is a K, chlorine is Cl, calcium is a Ca, magnesium Mg, iron is Fe. I know, for example, iron, why is Fe, because in French is a fer, and this is being named because in French is a fer, F-E-R, on the zinc, cobalt, and manganese, copper and manganese. So we consist of one or two letters. This is what is the chemical symbols. And we group those symbol, those elements by their chemical symbols in a table that we will call periodic table. I am not asking you to memorize these periodic tables, but I want you to know how to read a periodic table. If you realize it, the elements are grouping presented by increasing atomic number. So if you go from your left hand to the right hand, you see inside of each square those Arabic number 1, 2, 3, 4, 5, 6, those atomic number, increasing atomic number. And then in each column, you have the Roman number on the top. I will come back to those Roman number later on. This is what they represent, the number of the electron that exists on the last shell. We call that valence electron. For example, this column have one valence electron. This column have two valence electrons, three valence electrons, 4, 5, 6. All right, and then you have those rows. One row, second row, third row, fourth. This is the number of shells that those element has. For example, hydrogen and helium have only one shell. Lithium and carbon, oxygen, nitrogen, neon have two shells, three shells, four shells, 5, 6, 7. Okay. Another thing that I want you also to know how to, I want you to add it to your periodic table, is to be able to differentiate between metals and non-metals. You are going to do, you came here at the, we've designed this chemical element B, all right? And you're going to make a zigzag, stairs, and you keep going. And once you make this zigzag, you are going to separate between non-metal and metal. Retain that because this is very important, how those elements interact with each other. Remember, all the molecules, all the compounds are made of those elements. They are made at least two atoms coming together, they will make a compound. And those atoms, they came from where? It came from this periodic table. So how this atom, for example, that is calcium, is going to interact with bromine, for example, or the sodium chloride. The sodium is here, so it's going to interact with the chlorine, that is a gas. How? So this is how we are going to study later on how molecules are made. And in another word, what are the intra molecular bonding that exists between one element to another element. There are two. We are going to talk about it later. So they are actually, those are 96% of our body weight are made of oxygen, carbon, hydrogen, nitrogen. You have to retain that, okay? And 4% are made of calcium, phosphorus, and this vary. This is human over here, right? This is, but all the living thing, all of them, viruses, bacteria, human, animal, plant, they are all made of carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. And all the organisms do not require the same elements in the same quantity. Look at human. Phosphorus and sulfurs represent only 4%. Some bacteria, they will represent 90% the sulfur. They are sulfurous bacteria. 90% of their body is made of sulfur, but only 4% in the human. What's made 96% are oxygen, carbon, hydrogen, nitrogen. But all the organism, living organism, or a living thing are made of carbon, hydrogen, oxygen, phosphorus, and sulfur. They have some elements that they must exist in the human body, but they are representing what we call the trace elements. Those are required by the organism, but only in minute quantity, which is mean very, very, very low quantity. And one of them, which is the most important one for the human body health, is the iodine. And he is only, if you look at the iodine over here, this is one of the minute quantity of the human body. Iodine. And iodine, can cause disease, deadly disease, water, like these poor ladies here. So now we are going to focus on the atomic structures. We know now that atoms are made of particles. They are protons that they are positively charged, electrons that they are negatively charged, neutrons that they are neutral. They don't have any charge. I want you also to retain that positive and positive repel, negative and negative repel, positive and negative attract each other. All right, cool. So now let's see where those we have them. They are going to come together, those particles, to make an atom. Emergent properties, atom, all right? So where they exist. proton, if you protons and neutron, they exist in the center of an element. We call that nucleus. They are together, protons and neutrons. And it's so funny, they are clustered together. Protons is positive, and they told you that positive and positive repel. So why they don't repel when they are clustered together inside of the nucleus? Because of the presence of the neutron. Exactly. Neutron is between them to not let the proton be repelled by the other proton. Wonderful, cool. And their molecular weight is as big neutron as a proton. This is why, if you look at how symbolically has been here illustrated, almost the same size. All right. Electrons are very tiny. So we don't really know exactly where they exist, but all what we know that they are circulating around those center, this nucleus where the proton and neutrons exist. So they are in an empty space. That we are going to either symbolize it planetarily or by orbitally. And I come back to this in few minutes. So let's how if you look at if we go back to our periodic tables, those elements, you see some numbers in the top of them. You see, for example, H have a 1, helium have 2, lithium have 3, sodium have 11, potassium have 19, calcium has 20. What are those numbers in the top of them? And sometimes you see also another number in the bottom that is much bigger. Like sodium has 11, but you can see also that sometimes you write 23 in the bottom of the sodium. 23 is the mass number for the sodium. So this is symbolically how we proceed. We put the symbol, the chemical symbol, and we put this number and this number. So the atomic number is the number of proton. This is what is it. This 11 that you see, and this sodium sometimes is in the top, sometimes is in the bottom, but here is how you are going to figure out. Any times this number exists by itself, that's the atomic number. If it exists with another number that is bigger than this number, that means the other number, if it's bigger, that's the mass number. So anyway, so the atomic number is the number of proton, right? And this number over here is the mass number, right? So what's that mean? That's the number of proton and neutron. That means that's the weight of the nucleus or the element in Dalton. Why I neglect electron? Electron is so thin that his weight on the element is neglectable. He's not adding too much on the weight of the element. So when I weight an element, I consider the proton mass and the neutron mass. In another word, I consider only the mass of the nucleus of this element. If you look at the sodium, I don't see any charge. I don't see sodium plus or 3, 2, 1 plus, 2 plus. I don't see any sign in the top. So that means the element doesn't have all of it, doesn't have any charge. He didn't lose electron, he didn't gain electron. So that means if I have 11 proton, which is 11 positive charge, I must have 11 negative charge to neutralize it, right? So if I have 11 proton, that means I have 11 electron. So just by looking at the sample, I deduced that I have 11 proton, 11 neutrons. Now, how many neutrons I have? I just explained to you that 23 is the mass number, is the number of proton plus the number of neutron. Number of proton, I know it, it's 11. So 23 minus 11 equal 12. Therefore, number of proton equal number of neutron, it's a 12 for the sodium. And remember that the atomic mass, it's approximatively the mass number, but you add a unit, Dalton. That's atomic. When you talk about atomic mass, you put this is 23 Dalton. When you said just mass number, you just give the number. It's a mass. You need only a number. 23, mass number. All right, so I want you to train yourself over here. I give you a few seconds. Let me take the zoom. Here a second. So the number for proton on the oxygen, I have O, which is oxygen. I have 16 and 8. Which one is the mass number? Is 16, the highest. Which one is the atomic number? Is 8. So number of proton equal atomic number, which is 8. I don't see any charge, so therefore electron is also 8. Neutron is 16 minus 8, which is 8. Phosphorus, the mass number is the highest number, which is 31. 15 is the atomic number. Proton equal 15. Electrons, I don't see any charge, so equal also 15. So I have as much 15 positive charge as much as negative charge, which is going to be 15. So this element doesn't show any charge. And the neutron will be 31 minus 15 equals 16. The zinc, proton 30, exactly, electron 30, neutron 35. Now we are going to talk about elements that they have the same number. I repeat, the same number of proton, that means the same atomic number, but they don't have the same mass. And the mass number is proton plus neutron. That means what you change is their number of neutron. All right? We call that isotope. They have the same atomic number, but not the same number of neutron. Therefore, their mass number is increasing. Look at carbon 13, look at carbon 13, look at carbon 12, look at carbon 14. Carbon 12, of course, the highest number is the mass number, the lowest number is the atomic number. The carbon atomic number is always 6. The number of proton represents this element. You cannot change it. And this number 6 is specific only to the carbon. You are not going to see another element in the periodic table that has also an atomic number of 6. You are not. The atomic number is specific and characteristic of this element. If carbon is 6, you are not going to see another element 6. All right? So if you have 6, they have no charge. So 6 proton, 6 electrons on all of them. On the carbon 12, 13, 14. They are all having 6 protons, 6 electrons, 6 protons, 6 electrons, 6 protons, 6 electrons. What about the neutron? The first one is 6, the second one is 7, and the third one is 8. So you are seeing that the isotope, their number of the and the mass number increase. So in the same way, we are going to train ourselves over here. And now we are going to talk another type of element. Ion. We talk about isotopes. They have the same number of proton, but not the same number of neutron. Now we talk about ions. Proton will never change. The number of proton on an element it's very constant. You will never change it. An element has a specific number of atoms. We never. What is changing? We see it, neutron. In this case, we call those isotopes. They are like the same family of carbon, but they are brothers, siblings, all right? And now we have another type of sibling. We call that ions. Their number of electrons can change. The number of electrons can change. An element can either lose electrons or gain electron. When he loses electron, the number of electrons in his body will decrease when he loses electrons. And electrons are negatively charged, correct? And protons are positively charged. In this case, you are going to see more positive than negative. It will be called cations. Cations. When he gain electron, that means he will have more negative charge, more electron. He will be called ions. So let's train ourselves on an element X. If you see the first X in your left, he gained 2 positive charge. Wow. And I have symbol X, I have 65, which is the mass number, and 30, which is the proton atomic number. So atomic number equal 30. Neutron equal 35. The problem came with the electrons. How many electrons he lose? He lose 2 electrons. So 30 minus 2 equal 28. Another element, in this case, he's 3 times negative, so he gained 3 electrons. Number of proton equals 7. Number of neutron equals 7, 14 minus 7. Electrons, however, he is negatively charged. He gained 3 electrons. So he has 7, but plus 3, which is 10 electrons. So we're going, now we know what is isotope, ions, where the proton exists and where the neutron exists. We're going to focus a little bit on the electrons. Electrons, they exist, we are going to making it like they exist in orbits, all right? So we're going to make them like exist in shells. We realize that the first shell can only carry 2 electrons, which is wonderful because I can put an electrons in one pole and the other electrons in the opposite pole. And they will never repel each other because one is in one pole and the other one is in the opposite pole and they're circulating around the nucleus, no problem. So in 2D dimensions, I will see my electrons in shells, in circumscript circles. One second shell can hold only 8 electrons, right? The problem came with the second shell. I have to put 8 electrons on it. It's too much. You know that electronic storm is very, very dangerous. In the desert, when electronic storms happen, flights cannot fly over. They will expose. This is very dangerous. Just to tell you how dangerous an electronic storm exists. Without any rain, without any water, it can happen. That's the most dangerous storm that happened in the desert because of electron. So the second shell, let's focus on the second shell. We came up with some things imaginary in a 3D. We come up on the 3D axis. It's a 3D dimension. Of course, we have 3 axes, X, Y, Z. And we try to put orbitals, all right? And we are going to put in each axis orbital, like for example, this is Y, this is the first orbital over here, and this is X, and this is Z. So we are going to put electrons on each pole, and they are going to circulate without a repellent with each other. So the second shell has subshells or orbitals. Here have an orbital that is 2s, 2 for that it's the second circle, second shell, and s for orbital s. The first shell have only one orbital s, one. S orbital exists in any shells from the beginning to all the elements. All the shells of the elements, the first orbital, which is the S, exists, the S orbital exists in all of them. The second orbital, which is the 2s, exists on 2, second shell and up. And after that, I have another orbital that is called a P, the one that have X, Y, Z. This one exists from second to up. Then I have another orbital, which is D. That exists from third to up. So when I ask you to write down this element in orbital form, this is how I want you to write it. 1s, 2s, 2p. And if you have a 3 shell, is again, the s orbital exists in all of them. 3s, 3p. And then it's 3d because d exists on the third shells and up. So let's look at the neon, for example. The s as orbital can carry only 2 electrons. So anytime you see s, you put in the top of it 2. 1s, 2, 2s, 2. The p orbital can have 6 because I will put 2 in the suborbital x, which is the axis x. I can put 2 in the axis y, and they can only put 2 in the z because I will put 1 on each opposite suborbitals. All right. By doing this diagram, the second dimension, the shells, second shells, third shell, I will place the electrons. I will see the last electrons exist in the last shell. This is what we call valence electron. Valence electrons are those electrons that exist on the outermost shell, the last shell. And those electrons has the highest energy, and they are the ones that they are going to be involved in the chemical bonding. Those valence electrons, therefore, they will determine the chemical property of an atom, how it interacts. And the periodic tables, if you remember those Roman numbers, they show not only the shells that they have, but also the valence electrons that exist on the last shell. For example, the hydrogen have only one shell, and you have one electron's valence. The helium have only one shell, he have two. Lithium has three, he have two shells. So that's meaning the first shell has two, because he cannot have more than two, and the last shell have one. Right? The carbon have four. Atomic number is 6. So the first shell have 2, the last shell has a 4. Therefore, he can make like 4 bonding with other elements. Helium. Helium have 2 in his last shell. He have only one shell, and he have 2 on it. That's the maximum that this shell can carry, because the first shell can carry only 2. The neon have 10. The last shell has 8. This is why I put 0 over here. They are stable gases. They are noble gases. Those, they cannot interact. They are stable. They are not going to interact with any other element. Those are not stable, between parentheses. Right? They can interact with each other because they are either losing electron or gaining electrons. Why? Because they are all trying to obey to Octet rule. They are all trying to be as stable as they can. This is why we call the Octet rule. The Octet rule is that atoms generally react by gaining or losing or sharing electrons in order to achieve a complete offset of valence electron. The atoms that they have outer shells containing 8 electrons tend to be inert or stable. So this is why the noble gases are extremely stable. Remember when I told you to separate the periodic table by this zigzag, metal versus non-metal? The sodium, for example, the metals are tendencies to lose their electron valence electron to obtain the configuration of the nearest noble gas. So the sodium has tendency to become a cation, which is going to be more stable than the atom sodium itself. And the chlorine has tendency to gain, he has to gain an electron to become nearest noble gas neighbor. So he has tendency to be an anion chlorine minus. So we are going to come to the next part of this chapters, how we make a molecule. So let's focus on the sodium chloride. They can make those, by the way, those are compound, those bonding, there are 2 principal bonding. They are either going to share electrons, we call that covalent bonding, covalent bonding, or ionic bonding. What is the difference? Ionic bonding involve, they don't share it. One element will attract or will take the electron of the other element, and the other element will give this electron. This is involve electrical attractions between atoms. This is why I want you to know the zigzag between metals and no metal. It's like sodium and chloride. Sodium is metal, chlorine is no metal. So the sodium has tendency to lose the electrons, and the chlorine has tendency to gain this electron. And they do it by ionic bonding. The valence electrons of chlorine is 7, and the sodium, the valence electron is 1. So he has tendency to lose these electrons, become sodium plus, and the chlorine has tendency, he has to gain this electron. He has 7, he need only 1 to obey to Octet rule. So this is ionic bonding. Covalent bonding is the share of pair of valence electrons by two atoms. They can be either single, double, they can be polar, non-polar. I mean, covalent bonding is like, for example, they have between two atoms that they have the same property, hydrogen and hydrogen. You think that one of them will take the electron of the other? They are trying to obey to the Octet rule. They have only one shell. Octet rule, they have to have two electrons on this shell. They have only one. So they are going to make a peace. They are going to share the electrons covalently, and each element think that he is stable. This is what they are doing. Covalent bonding exists between the same nature of atoms, or if they are both gases or both metals, they are going to share. None of them is going to attract the electrically these electrons. Take it. All right, between the oxygens, between each other, the molecule of water, oxygen and hydrogen, the methane, carbon and hydrogen. And I said this bonding can be either, and this is the way we rated this covalent bonding. We rated either by 2 points, look at that, or one little line like that. Either by 2 points, that's mean a pair of electron is shared over here, or one line over here, that's mean a pair of electron is a share over here. Double bonding, that's mean each two dots over here, it's a pair of electrons. Or double bonding over here, which is two pairs of electrons are sharing over here. Okay? So if we look at all the elements, we have the hydrogen can be one bond because he need only one electron. The oxygen, he has 6, so he need 2 more electrons, so he can make 2 bonding. Or one double, either single, 2 bonding, single like H with 2 atoms of hydrogen to make H2O, or a double bonding like with another atom of oxygen, a double bond oxygen, and each atom think that he is stable. They are sharing electrons. So in a molecule of water H2O, the hydrogen, he share the electron with the oxygen, and he is becoming like kind of stable, and the oxygen also he's sharing electrons with the hydrogen and with the hydrogen, another atom of hydrogen. The nitrogen can be 3 bond, and the carbon is the one that is tetravalence over here. He can have possibility to make 4 bonding. So therefore, covalent bonding involves the sharing of electrons. Ionic bonding involves the electrical attractions between atoms. All right, but we hear about covalent polar and covalent nonpolar. What's that mean? That means they have some, they are bonding with each other, but they create what we call polarity. And that's came because one element, even if they share electrons, but one element is more electron negative than the other element. And this is why when they share the same electronegativity, they interact to form nonpolar. They are not creating this polarity, nonpolar covalent bonding. So to understand this, I want you to look at this hydrogen with the hydrogen. They are equal electronegativity. This is the same atom. One have one electrons, the other one have one electrons. So they have the same electronegativity. The bonding between H and H over here, the single bond that is existing over here, H, this little underline, and H, this is covalent bonding, but it's nonpolar. All right, nonpolar covalent bonding. Polar covalent bonding, if you look at chlorine with hydrogen, chlorine have 7 electrons, unbalanced electrons, and hydrogen have 1. Who is the most electronegative? Of course, chlorine. All right, it's covalent, no problem. They are sharing the electrons. But since this side is more electronegative than this side, the electron, he have more mass, this chlorine, in his nucleus. It's very heavy. So the electron of hydrogen has tendency to be more closer to the nucleus of the chlorine than his own. So, and therefore, this is why you're seeing this. This is covalent, but you're seeing this. So they create some polarity over here. The overall, it's not charged, but they create a pole that is slightly negative and a pole that is slightly positive. Slightly negative because the electrons of hydrogen over here have tendency to be more close to him, to the chlorine. And the hydrogen seems like he loses his electron, but he's not. He's not losing the electron, but his electron is like more attracted to this pole where the chlorine exists. The overall molecule HCl is not charged. It doesn't have any charge, but you create this polarity, slightly negative, slightly positive. This is what I call covalent polar bonding. Covalent polar bonding. So when the atoms are equally electronegative, they will interact to form nonpolar covalent bonding. When one atom sharing electron is much more electronegative than the other atom, the covalent bonding is likely to be apolar. We came up to next part of this chapter, which is now how a molecule will interact with another molecule. We know how atom will interact with another atom to make a molecule, either by covalent or by ionic bonding, correct? All right, now how a molecule will interact with another molecule? Well, there are three types of forces. Dipole-dipole interactions, hydrogen bonding, and van der Waals or London forces bonding. Did you ever see this? I always call it a gecko, which is this little gecko laser. You see it that is in your roof, and he's not falling down. And when you look at his feet, he have this little hairy thing that will attach to the roof. This is actually, and if wind came in or something, he will fall down because of this. This is van der Waals. This is some molecule that they are in the air that they will interact with the molecule that is in your roof. This is like molecule interactions, and it's van der Waals forces or London forces. Very, very weak. This is why when the hair came in, it just fall down, or you can just attract it with your hand and got it in it. And then we have a hydrogen bond. I want you to see the water now. This is a molecule of water. I always call it Mickey Mouse hot. Did you see that? you have oxygen, hydrogen, hydrogen, they are all gases, so they are going to bond covalently. Oxygen will covalently bond with the hydrogen, and the other hydrogen is also covalently bonding with the oxygen. Okay, well, no problem. Who is the most electronegative? Now, of course, the oxygen, the valence electron is 6. The hydrogen, each hydrogen, the valence electron is only 1. So this is the most electronegative, all right? So the hydrogen electrons have tendency to be more closer to the nucleus of the oxygen for both, all right? So this is where you see the hydrogen is completely like getting inside of the oxygen. You see these illustrations did on it, the way is like hydrogen is like getting inside of this ball of oxygen, and therefore they create a polarity. So this bonding over here between oxygen and hydrogen is called covalent polar bonding, covalent polar bonding, okay? And this is because it creates pole that is slightly negative and a pole that is slightly positive. The overall, I repeat, the overall molecule is not charged. This is neutral, all right? But it's slightly create those polarity. So, and this property will allow this molecule to interact with another molecule. Look at the ammonia molecule, NH3. NH is more electron negative. The valence electron is 5. The valence electron for each hydrogen is only 1. Again, he says create also polarity. Remember what I told you in the beginning of this chapter, positive and negative attract each other? Correct. All right. So this is how this molecule of water will interact with this molecule of ammonia. By this property of positive will be attract to negative. So the pole, you get it. The pole that is slightly positive will interact with the pole that is slightly positive. And this pole to another pole interactions, which is a dipole-dipole interactions, it's called in this case hydrogen bonding because it involves hydrogen in one of the molecules. It involves hydrogen. So this hydrogen will bond to the slightly negative of the other molecule, pole of the other molecule. And we call it hydrogen bonding. Be careful. This hydrogen bonding, not only he is involved, but he has to be within this molecule that bring it in, covalent and polar. This is why we call it hydrogen bonding. So hydrogen bond interact with neighboring is really part in a polar covalent bonding. This is one of the strongest intermolecular force. And can you believe this is this hydrogen bond that will make water that you are drinking? Water. I will again talk about this part of hydrogen bond property when I will study the next part of this chapter, which is going to be the property of water. So let's talk about chemical reactions. Chemical reactions is all the metabolic reaction that happen inside of our body is a chemical reactions, and chemical reactions start with a reactant and end up with a product, reactant, product. And it has to be stable. The rate of the forward reaction should be equal to the rate of the reverse reaction. So let's see, for example, I have here 2 atoms of oxygen, red. I end up having 2 atoms of oxygen as products. I have 4 atoms of hydrogen. I must have 4 atoms of hydrogen. It has to be balanced. If I start with 4 protons, 4 4 atoms of hydrogens and 2 atoms of oxygen, I end up having 4 and 2 as a product. So it has to be balanced. Okay, the rate of forward reactions equal the rate of the reverse reactions. With no effects on the concentration of the reactions and the product. Okay, so we are going to continue later on with the properties of the water. We'll see you next time. Thank you so much.